right, welcome to Energy Systems. Caught me by surprise, this engineering technology, safety and construction job fair, internships, and beyond. For you guys, it would be recruiting. There'll be another one in the fall, but it won't be as well focused on what we do. There'll be some people there. This is more focused on us. Then it says it's October 8th, which sort of surprises me that normally it's a November thing. So on your syllabus it says November. Provide time to go make sure that you are able to do that because it happens during school time or class time. So, where are we? Oh, good.
Yeah. Yeah, box.
Whoops. We were working this problem, and we got this far, but we haven't gotten quite that far. And I'm also going to do one more thing, and that's what is the mass flow rate, which would be the other thing. And all these properties were like intertwined, so you can't just change the temperature, and if you change the temperature, the speed would change, but in order for the temperature and the speed to change, the area has to change. They're all interrelated. So, I'm probably going to have to zoom in on this. Where are we now? Coming up with the document camera. Yes. Oh. I know why. That's why this is sitting here. Somebody unplugged it. You can hope. Hello? No? We'll try that plug. Oh, look at that. Something's happening.
Yay.
So yesterday we were working on this thing. And if it's true that the mass going in equals the mass going out, what was the mass? The mass is a volume flow rate times density gets you a mass flow rate. Because depending on how dense it is, it has to do with how fast it's going. So volume flow rate is the velocity times an area. An area, how fast is it expanding? That'll get you a volume flow rate times density. But in density in our version of ideal gas law, it's P times specific volume, PV equals RT. This is the inverse of density. So if you solve for density, and density is absolute pressure divided by R times T. Absolute temperature, ideal gas law. So I'm going to stick this, plug it into that equation, and that's what I did here. So that's what the mass at point 1 is velocity 1, area 1, pressure 1 divided by temperature 1 times the R equals mass flow rate. But at point 2, it's the same thing. So it's just substitute 2's in there. You get V1, A1, P1 divided by T1 times R equals V2, A2, P2 divided by T2 times R. Well, they're both, I can divide both sides by R, multiply both, whatever. The R's are going to wash out. We don't have to worry about the R for this case. Because area, what we're looking for is area on the outlet. We know the velocity, we know the pressure, we know the temperature. So we're going to solve all those and bring it back. Area to ratio of velocities, ratio of pressure, sort of the inverse ratio on temperature, times our area 1. We don't even, these need to be absolute values here, but they give it to us in terms of atmospheres. We don't have to turn it into any other set of units. It's still a ratio. The units still cancel. So, conservation of mass and ideal gas law got us to the point where you do this ratio and those units cancel, this ratio, those units cancel, this ratio, those units cancel. All these ratios times inlet size should give us a different number. So that's going to be 1/5, and that's 1/8, and that's not so much. 1/40, I don't know. 1 1/4 cubic feet-ish. Or square foot. Anyone have numbers on that?
About 110.
So what did we get again?
110.
110?
1.110.
Oh, yeah, 1/10. Yeah. 0.103 square foot. In order for the outlet to go as fast as we said it was, in order for it to be the outlet temperature, in order for it to have that outlet pressure, that size nozzle is going to give us, so it's going from down 1/50th the size, but it went from 50 feet per second to 288 feet per second, which is pretty fast. So that's a nozzle thing. So we've answered the question, how fast is it going and how big does the nozzle have to be for it to go that fast? Another question we could ask is, what is the mass flow rate through it? Just exactly how big is a fan would we need? And now we'll need to do the calculations. I'm going to do for the inlets, about 50 feet per second. And it was all going into 5 square feet. I'm going to do this one off on the side for my density. My pressure on the inlet was 10 atmospheres. I'm going to go with 147, that's 14.7 pounds psi, 1 atmosphere times 10 gets 147 pounds force per inch squared psi. Oh, yeah, and that's an absolute pressure. Everything else is in feet, so I'm going to have to turn this into pounds per square foot. So I'm going to say 144 inches squared is 1 foot squared. We got a value of R, 53.3 foot pound force per pound mass, 3 Rankine. My inlet temperature, T1 in Rankine degrees, was 619 Rankine. So inches squared cancels. We have feet in the bottom here, and we have feet there. We're going to end up with foot cubed in the bottom. Have pound force here and pound force Rankin's cancel. We got pound mass in the bottom of the bottom. We're going to units of pound mass per cubic foot. Does that sound like units of density?
No.
Which is what we're looking for? It doesn't. Not at all. Not in your book.
Is this from, this isn't from the homework, is this?
No, this example. This
Oh,
example.
okay, I was like, it looks familiar just because of the equation right up there.
Yeah.
A2, yeah, for the last problem.
Yeah.
So I was a little confused with the numbers there.
Yeah. I don't know if it's the same. No, I don't know if it did the same numbers.
Oh, no, the number is definitely not the same.
Yeah. I'm looking for the density to put in here. What we're taking to see just exactly what is the mass flow rate for that problem. And we're doing it from the inlet, because the outlet's the same as the inlet. So that's going to get us, when we crank through the numbers, we're going to get the density of air at 10 atmospheres at whatever temperature involved, this temperature. So what have we got? 147 times 144 divided by 619 and 56. Golly, I can't even estimate that one.
0.64.
0.64. We got more digits on that.
Yeah, 159.
We're really only good for maybe the 3 digits, but we'll use all those. So we got 0.641. I'll call it 16 pound mass per foot cubed. And there's foots cubed. And we get units of pound mass per second. Call it 160. We have agreement on that?
Yeah. I agree.
So that would scale up. All those things are interdependent. We kind of broke them apart and started solving this with conservation of mass, conservation of energy, and ideal gas law. The kind of a good problem for all that. This is a simple sort of problem for compared to what it would take if you start going fast enough that you get into supersonic flow or approaching sonic speed of sound. Speed of sound is really the rate at which energy can propagate through the molecules of the air. It changes with temperature because the temperature changes the density, etc. And when you get close to that speed, you'll actually get a shock wave. And they design aircraft engines for cruising for that shock wave such that the pressures come in really fast. It doesn't blow through the engine. It comes up to a place where it nozzles down to the point where it goes essentially sonic, but what it does, it creates a shock wave, and then it pressurizes the engine. It changes it from speed to pressure. And then that sort of, the speed that the air is going generates the pressure inlet for the compressor side of the turbine. It's not like the turbine blades have to deal with, sonic speed air coming at them. They just get pressure because the nozzle will choke. It chokes at that speed. I don't know that much about that other than it happens. When it chokes, you can't get more through. There's a limitation thing. Anyway, that's what that's about. Any questions on that? Okay. New topic, another topic, thermal type topic. And that's gas mixtures and partial pressure and partial volume. This is important for, in particular, when you talk HVAC, the moisture content in the air, the partial pressure is going to have a lot to do with how that works. Other things too. And you can talk in terms of a mole fraction or a mass fraction. For our purposes, when we're talking partial pressure, it goes back to the ideal gas law, which is about moles of gas, not, the number of molecules, not how much they weigh. And if you do go back to the basic ideal gas equation, and you PV equals nRT, if you have 1 mole, which is 1 gram mole, which is 6.603 times 10 to the 23rd things in a bucket, and it's at atmospheric pressure and atmospheric temperature, standard temperature and pressure. That takes care of pressure, temperature. You got R as a constant, N you just designed as 1. If you crank all those and solve for volume, you're going to always get 22.4 liters worth of volume for 1 gram mole. And that doesn't matter if it's helium or it's water vapor. It doesn't matter if it's uranium dioxide gas. It doesn't matter if it's xenon. They'll all have different weights because the molecular weight of those gases. But the weird thing about ideal gas laws, at the standard temperature and pressure, if it's an ideal gas, it'll be 1 mole will be 22.4 liters. So, mole fractions are what we use when we're some of these things, not the mass. And if you had a mixture, in this case, the mole fraction is how many moles are there out of the total mole of a mixture of gases. So if you have an air-fuel mixture, like propane and air coming in, and you keep the air-fuel mixture right, you can say what the mole fraction of the propane is, like inlet to something. The sum of all the mole fractions is going to be 1. Why is that? Because 1's third, 3/4 of them, and then 1/4. If you're missing something, then it won't come to it. Whatever you got is always going to add up to 1, percentage-wise. And the mass fraction is going to be different from the mole fraction if they have different molecular weights. So let's figure this out. I'm going to make a table. And let's see, in my table I've got H2, I've got N2, CH4, I've got mass. So I got 3 kilograms, I got 5 of hydrogen, I got 5 of nitrogen, I've got 12 of those. Molecular weight, moles. And what is the molecular weight of a gram in gram moles for hydrogen? Hydrogen's 1.00794. We're going to forget about the 794 part and just say it's H2, right? And 1 H is 1, so it's 2 grams per mole. And that would be the so-called gram mole. Nitrogen. Nitrogen is 14.0067. Forget about the 0067. It's 14 grams per mole, but it comes in two, so there's two of them. We got, what do you think, 28? CH4. Anyone want to hazard a guess on that? I'll give you a hint. Carbon's 12.
16.
I like that. 16 grams per gram mole. So, if it's 2 grams per, standard temperature pressure, that'd be 2 grams will take up 22.4 liters. We've got 3 kilograms of it. How many moles do you suppose we have? How would we do that? 3 kilograms times, or divided by 2 grams per, we saw 0.002 kilograms per gram mole equals something. Anyone want to hazard a guess on that one? Yeah, 1,500 sounds right. And likewise, for this one, 5 kilograms divided by 28 grams should get me something like 178 gram mole. Oops. How about the next one? $12 divided by 16 is going to be less than 1,000.
750.
I like it. So here we got 12 and 5, 17, 3. We got 20 kilograms. What's how many moles are we dealing with? 22, 50, 23 and change. Anyone have that one?
24, 28.
So, what is the mole fraction for H2?
Point 62.
0.617.
617.
I'm going to go with 3 digits and call it 0.618. And the 178 divided by 24, 28.
0.073.
And 750,
1309.
309. And if you add all these up, 6, 7, 8, 9, 7, 8, 9, 10, I bet you're going to come up with 1.000. So it's 7% of the number of molecules are nitrogen. 31%, 31 out of every 100 molecules is CH4. 7 out of every 100 molecules is nitrogen, and 62 out of every 100 molecules is going to be hydrogen. Now that part, that wasn't so hard, was it? the ramifications of this are pretty, they're big. So we just found all that stuff. Because it directly, the number of molecules is related to either a concept of partial volume or partial pressure. And if I draw a box, I'm going to draw it for air now. I don't know if you can read that, but air, we can say, is about 79% by molecules. Nitrogen is about 21 by molecules. The mole fraction 0.79, actually 0.78, and everything else is 1%, but we're going to lump it into nitrogen. About 21 out of every 100 molecules of air is oxygen. We'll say 79, so it's 78, and then a bunch of other argon, CO2, water vapor make up the other 1%. But if I was able to put a little divider in here, in that box, and I could divide the box with this little divider, and there's a little hole in the divider, and every time an oxygen molecule comes by, I grab it and put it through the hole, and keep doing that, and all of the oxygen molecules come by. I could separate it such that by the time I'm done, I would have 21% of the volume would be O2. And 79% of the volume, so this side would be O2, this side would be N2. If I could separate them, that's the way it would come out. And now, magically, I'm going to cut that box. This was like 1 cubic meter to start with. And I take that, and now I've got 0.21, or 21 liters, essentially, is oxygen, and 79 is nitrogen. I can cut that box and take it into 2 boxes, and it's all these magic boxes. If this was at 100 kilopascal standard atmospheric pressure to start with, now I've got a box that's 79 liters, or whatever it is, 790 liters, 1,000 liters to a cubic meter. 79% of the cubic meter is at atmospheric pressure with nitrogen. If I take that box and I expand it back out to 1 cubic meter, what will happen to the pressure of the nitrogen? It goes down. PV equals RT. And if the pressure was 100 and we had 79%, and now if I make the volume out to 100%, that means the pressure has to go to 79 to be the same number. So I can say the partial pressures, or the partial volume is 79%. I could also say the partial pressure of the gas in that whole meter is 79 kilopascal. If I took the oxygen now, I took its box, I cut it off and had its box, and now it's only 21% of the volume, and I expanded it back out to 1 cubic meter, its pressure is going to drop again, and if it was 100 kilopascals at 210 meter, 0.21 cubic meters, and now I make it go out to 1 cubic meter. It's going to have to trade. It's going to be a partial pressure in that box now of 21 kilopascal. It turns out in the air, that partial pressure thing works even when they aren't separated. The partial pressure of oxygen in the air right now is 21 kilopascal, thereabouts. It's 21% of atmospheric pressure. That's what drives the oxygen into your lungs. CO2 concentration is high enough, it goes back the other way. That's why when you climb a mountain that's 30,000 feet tall and the pressure drops to 1/3 of atmospheric pressure, the oxygen, there's a limit to how the pressure at which oxygen will exchange in your lungs. It's harder to breathe at higher temperatures or higher altitudes because the overall pressure is less, which also makes that partial pressure less. This ends up getting used that concept gets used for a bunch of things. It explains a lot of things like weather. You got the same air and you have high pressure and then suddenly you get low pressure and that changes the partial pressure of the water and then suddenly it becomes, instead of being below the saturation point, suddenly it becomes saturated, which means it starts to condense out of the air, which means you get clouds, and if it gets enough of it, then it starts raining, just from atmospheric change based on the partial pressure of the water vapor in the air. So, partial pressures are really, really cool. And the mole fraction, it will be the pressure fraction, it's the volume fraction, aside from being the mole fraction. Which also means if you can figure out the pressure fraction, that will tell you the mole fraction. And sometimes you can figure this out by finding for instance, we can figure out how much moisture is dissolved in the air by chilling down the air until it gets a piece of the air until water starts to condense. If you know the temperature at which the water starts to condense on something, the dew point, that says it's the saturation temperature for the pressure of the water vapor. You got to the saturation, found the saturation temperature for the partial pressure of the water. If you know the partial pressure, then you know how much the mass of water that's in the air. You know the number of moles per total thing, and then if you know that, then you can back into just exactly how much mass of water is in it by temperature. Drop the temperature till it makes water. That's the dew point. That's the temperature at which water. You can, in the middle of summer, you can have grass. In the morning it's wet. It didn't rain at night, but if it's a clear sky and there was enough moisture in the air, the grass will radiate heat faster than other things, and it'll radiate to a colder temperature than the air itself, and then water condenses on the cold surface, and it'll actually water itself even when there's no rain, kind of sort of. We call it dew point because that's where the dew comes from. Blah, blah, blah. This is sort of what I just went through, so we'll just take the next page. So the properties follow all that. Some of the properties you do per mole when you're doing those. If you know moles, you can get mass and then do it in terms of mass. I don't remember if we even use this much. But it starts to become, how it gets useful is for heating, ventilating, air conditioning. Turns out most of the load for heating, and especially for cooling, and for dehumidification, most of the load is the moisture of water in the air, because not only do you have to cool the water down, the water vapor down to saturation point, but it condenses, so that latent heat thing is, which is really huge relative to the actual temperature change. It becomes the largest heat load for air conditioning. So these two are partial pressures, the total barometric pressure. If you get this, if you drop the temperature to the point where the actual pressure partial pressure in the air is, drop the temperature down until the saturation temperature matches this, then you're going to, that's when that heat load, you start doing the latent heat, you're sucking the moisture out of the air. And that saturation temperature is in steam tables. For the atmospheric kind of temperature, the steam tables don't, they have those numbers, but they aren't as fine as we need when we're talking, the steam tables are kind of crude for doing HVAC. So we don't use the steam tables. We could, it's the same numbers, but 5 degrees, 10 degrees, we want to know, fractions of degrees. So there's formulas for that. The saturation, you can read it off the steam tables. I was looking into wind turbine efficiency at one point, didn't quite finish the project. Money dried up, but along the way I need to find out the power for a wind turbine had to do with the speed of the air and the density of it, and the density is affected by the relative humidity and basically about the moisture in the air. Because if you think about it, air is nitrogen, which is 2 times 14, and oxygen, which is 2 times 16. You got 28 grams per mole or 32 grams per mole, and it's more than 28 and less than 32. We call it 29 grams per mole. Anyone want to hazard a guess at what the molecular weight of H2O vapor is? O is
16.
and H is 1. Anyone do 2 plus 16 for me? We got 18. Now compare, is 18 more or less than 29? It's a whole lot less. So aside from temperature making it less dense, if you have more moisture in it, it will, higher, and especially in summer, at higher temperatures, you get more moisture in the air. You can have a lot less dense air due to atmospheric thing. It's not a lot. I mean, it was, somewhere from 0.5% to 2% difference in the density, which if you're looking at a wind turbine and you're looking for fractions of percent of wind turbine efficiencies, then it starts to become an issue. So I actually spent, probably most of the time I spent on that project was trying to find a good number for just exactly what can I put into a spreadsheet that'll give me the saturation pressure. If I get a temperature and I get the saturation pressure, then they'll give me relative humidity, which then I can turn into, I need that for my density. So, saturation pressure is actually this many kilopascals, 6.611 times 10 to the 7.50 times temperature of the air in degrees C divided by temperature of the air in degrees C plus 237. That isn't a typo, it's not supposed to be 272. That was a correction on the formula for it. And believe me, there's about 49 different papers that present different ways of coming up with this This is a formula. You just give it temperature in degrees C of the air. It'll tell you what the saturation pressure is. And then I believe it's relative humidity tells you what is the saturation pressure relative to the saturation. So this gives you saturation pressure and then relative humidity. If it's 30% relative humidity, then your actual partial pressure is 30% of this value. And now you can crank that into a density formula. This is actually, this is what National Oceanic and Atmospheric Administration uses in their, some of their calculator things. So, we've got moisture condensing from air at 15 degrees C. Got a partial pressure. I want to find out what is that partial pressure. We can do that with the formula, actually. What did I say? My units upstairs here need to cancel, and they do.
Can't see.
So the exponent is, this is like an exponential curve. It only works between certain limits. And if you go outside those limits, boy, does it get bad fast. But inside those limits, and it's at sort of minus 50 degrees C to plus 40 degrees C. 40 degrees C is pretty hot. Saudi Arabia probably gets hotter than that on a hot day, but not so much in the U.S., except maybe Mojave Desert or someplace. Got happy fingers going on that one. What'd you get? 2.72.
Got 1.7.
1.7? and
Oh, that's the power. 1.703.
okay,
Okay. Wow.
that was your power.
No. The function, the way you wrote it, I thought it was just like a flat out kind of thing.
Yeah,
That's the exponent. There we go.
that's the exponent. And if I look at our saturated table from the thermal book, I don't think your book, it may not have metric. If we go to 15 degrees, it's at 1.7057.
Yeah. Okay.
Three digits, we're pretty good. Next question I had there is what is it if it's 6? And we could solve that one solve it. I won't get into that, but basically, if we had a 6 kilopascal saturation temperature, it would be up somewhere above 35. Probably something like 36 or 30, probably 36-ish degrees C. That would be really high. It's not common that you actually see numbers that high for. I mean, that would be a huge rainstorm at 36 degrees C. 36 degrees C is not cold. What is that? That's like 100 and, that's like a tropical rainstorm on a really hot day. Yeah, that's crazy hot. It's like 100 degree Fahrenheit, 105 or something like that. So at 6 kilopascals, if there's that much water in it, and it started condensing at 36 degrees, the moisture, that's tropical. If it's condensing at that temperature, that's the saturation temperature. You would know that you had 6 kilopascals. So that's how we use that stuff. And that's actually the end of my slides for chapter 1. Now we've done all this basic thermal. Now the next chapter, we're going to do chapter 3. And chapter 3 is going to get into some chemistry and more sort of thermo stuff. But now we're going to push on and talk about combustion and where's the energy coming from. And when we get done with chapter 3, then we're just going to start using it. Then we're like into the meat and potatoes. But a little bit more of the background, and then we'll do the fun stuff.
Great.
All right, that's it.